2.4, number 132. We have a function f of x equals 2 on x squared plus 1. And the question says to determine any points where this function may be discontinuous and what type of discontinuity it is. Okay, so this one is extremely simple. Number 132 is continuous everywhere. Okay? So there are no points of discontinuity for this function. Its domain is all reals, and it is continuous on its domain. And the main way to tell is that usually with a rational function like this, you would be concerned where the bottom might become 0. That might be a point of discontinuity, infinite or removable. But in this case, if you check the bottom to be equal to 0, right, where's the bottom equal to 0? Immediately you come up with, you might say, imaginary values, right? You get x squared equals -1, which implies that x would equal plus or minus the square root of -1. That is, in another notation, plus or minus I. So there's no real value that makes the bottom equal to 0. So therefore, there's no real value to remove from the domain. The domain is all reals. There's nothing to take away. And since this is a polynomial, i.e. a rational function, it's continuous on its domain. So that's number 132. Number 133, though, is to continue with this. To give an example where there is something to kind of look for. So f of x now is what? It is x on x squared minus x. Yeah. All right. So if we factor the denominator to start looking for, you might say, problem spots for this function. A little sloppy there. And you get x times x minus 1. X minus 1. So we see the two problem locations, possible points of discontinuity will be at 0 and 1 respectively for these two factors. All right, I just need to see what's going on there. So 1, if I cancel the factor of x above and below, right, then the x equals 0 location looks like it's not a problem anymore. So this is probably a discontinuity which is removable. Right? Anytime you can cancel those factors, it's probably a removable discontinuity. I'm not guaranteeing that, but certainly whenever there's only one factor like this above and below, right, without going into too many details, that will be the case. It will be a removable discontinuity. But we'll show it using the definition in a moment. Just want to give a little heads up on that one. All right, so the 1 value, though, is causing an infinite discontinuity. If the factor is not removable, x minus 1 does not have a partner up here to cancel with, so therefore, for a rational function like this, certainly it's going to be an infinite discontinuity, but we'll show that as well. Let's just go through both of these. So the x equals 0 situation, x equals 0, what's happening there? All right, so we need to find the limit of this function x on x times x minus 1 as x approaches 0. Okay, so for all values that are not 0, the x's would certainly cancel, and so we'd have the limit as x approaches 0 of 1 over x minus 1. But now, again, because of the removable discontinuity scenario, what happens is that you plug 0 in, and you get, of course, 1 over -1, which is -1. Okay. So the limit of this function as x approaches 0 has a value associated with it. Now we just need to see what is the value at 0. Okay, what is the value at 0? Well, f of 0 does not exist. All right? f of 0 doesn't exist. So again, since the limit as x approaches 0 of our function equals -1 does not equal the function value itself, because it's not there, right? So therefore, discontinuous. At x equals 0, as we suspected. But since the limit does exist there, right? The limit has a value. Well, the problem is the function isn't there. So anytime the limit has a value, but no function value, or limit has a value, but the function value is different, either one of those two cases, then that's going to be a removable discontinuity. All right, so what about at x equals 1? So at x equals 1, what is happening? So we try to take the limit of this function as x approaches 1, and what happens? Well, for all, x isn't 0, so the cancellation still holds true, and we get a limit as x approaches 1 of 1 over x minus 1, but that means the bottom overall is heading towards 0, and we know that a finite value over 0, right, is going to be d and e, but a particular d and e is going to be some type of infinity. I don't want to go through which infinity it is right now. It's going to be different on each side, whether I approach from left or from right, and that's not really important for the discussion. The main point is you have an infinite discontinuity, right? So certainly this is discontinuous because the limit didn't even exist, right, because it's infinite. So it is discontinuous at x equals 1. And what type? It's an infinite discontinuity, clearly, because we got infinity, some type, which we're not going into at the moment, again, because it will depend on which side you're approaching from. But we still know what is going on. It's a vertical asymptote there. And every vertical asymptote is an infinite discontinuity.